Welcome to the third vodcast of Special Relativity for Unit 3 Physics of the VCAR study design. In this lesson we're going to be looking at the relativity of simultaneity. So there's a few syllables for you. And so the goal, as you can see, to understand why the concept of simultaneity is relative. So first of all, you might not know what the hell we're talking about with the word simultaneity. That means the idea of things occurring at the same time. So like simultaneous events being events that occur at the same time. So for example, you might be making a cup of coffee and simultaneously you're chewing on a carrot at the same time. Or some people might be driving and simultaneously they're texting at the same time. Quite likely within a short period of time after that they will be dead. So that's what we mean by simultaneity. And so to be able to talk about this kind of stuff with special relativity, we need to first of all get a simple but important definition straight. So in special relativity, we're always talking about events occurring and measuring those events. So we just need a quick definition, which is this for an event. So an event being something that happens for which an observer can measure spatial coordinates and a time coordinate. So the kinds of things we're often going to be talking about here are like when a flash of light occurs or something like that, just to try and keep it simple. And so when we do that, when we're measuring that event, we'll be saying the flash of light occurs at a certain position and it occurs at a certain time. So we need to assign spatial coordinates, meaning position, and a time coordinate. Now, just briefly, because it'll help us build a mental picture of how this works, it's good to try and think of in a theoretical sense, how we could make those measurements. And this is very theoretical, it's not at all practical, but because it does get quite confusing, it's helpful to think how we can measure an event. So if we are to measure an event, like I said, we need to be able to assign a time coordinate and a spatial coordinate. So what I want you to imagine is that in some frame of reference, and we've been talking about frames of reference in the last couple of episodes, where we have a coordinate system in that frame of reference. I want you to now imagine with that coordinate system, you have a bunch of clocks along it. And the point, and so this is what we have here. This is a coordinate system which can measure position. So let's say this coordinate system, it's 1 meter between each space, for example. So this is position of 0, this is position of 1 meter, this is position of 2 meters, this is position of 3 meters, and so on. But in our coordinate system, we've just got all these, bunch of clocks as well. And of course, this would be in 3 dimensions, but for simplicity, we'll ignore that. So there's clocks going this way, clocks coming out of the page as well. The irony of that, obviously, being that you wouldn't have time to get through all these clocks. Irony. So to be able to make these measurements, though, we're going to just ignore the practicalities of this situation and just imagine a theoretical situation where you can have these clocks so that if anything occurs, we can say it happened at this point and at this time. But in order to be able to say what the time is, we need to be able to synchronize our clocks. We need synchronized clocks. So what that means is that the clocks are all reading exactly the same time, precisely the same time. Now, what you'll come to understand later is that synchronicity, that ability to have the clocks all reading the same time will depend on your frame of reference, but we'll get to that later. So just within our frame of reference that we're looking at here, we're going to say that we want all of these clocks to be ticking exactly synchronized, so they're all reading the same time at a given instant in time. So how could we set that up? Well, just imagine that you have a whole bunch of helpers. So there's a person standing at each position, and that person is ready to set the clock going when they're given the signal. Here you are. This is you're in command. and you're going to be telling all these people when they need to set it. So you set the clock at 0, so your hand is reading 0, although I'm not going to draw this as an analog clock because it's just going to be annoying if I do. So I'm going to say t equals 0. You set that clock, and let's just imagine that when you do that, automatically a flash of light comes out of here, like this. Now the purpose of this flash of light is, and you need to understand, there is no way to instantly tell all of these people that you've set that clock. There's no way to instantly have them have that information. The fastest way you can do that is by telling them with light. So the instant that you set the clock at 0, imagine a flash of light comes out, and then this person needs to set the clock when they see that flash of light. But of course, it's taken some time, however small, for that light to get from here to here. And the amount of time that is, it's just a simple distance and time equation. So I might put this here. You remember that we can say distance, speed, and time. So I'm going to say speed, time, distance are related like this. So to be able to know what the time should be at this clock when the flash of light reaches this person, they need to do a calculation which looks like this. So the time that's passed is going to be the distance that they know the light has travelled, which is 1 metre, divided by the speed of the light. Sorry, I've made a mistake here, which was very clever of me. Not thinking. So the time that's passed is the distance 1 metre divided by the speed, which is the speed of light, which we know to be c. So that means that the time that this person will set the clock at should read t equals 1 divided by c, whatever that number is. And the light keeps passing through until it reaches this person, and for exactly the same reason, this person will set the clock at 2 divided by c. And just to be clear again, these people are setting these clocks at times later than the previous one. So even though what I'm showing here are different numbers, that's because they're at a different time, so that by the time they're all set, they are reading the same number in this reference frame. So finally this one will be 3 divided by c. Now this idea is something that will help us to be able to understand as we move forward in this lesson, and then in the next lesson, which will be on time dilation, and then the following lesson, which will be length contraction. It will help to be able to have this mental picture, to just imagine that we have this network of clocks in our reference frame which can all measure the time. Okay, so if we can understand that, our idea of synchronized clocks, then we're ready to start talking about what it means to have simultaneous events and why they're relative. So just from the outset, I'm going to make clear what the result of all this is going to be. And that's this. We're going to prove that if two observers are in relative motion, they will not agree as to whether two events are simultaneous. So you might hear a crash occurring in some position, and then at the same time some lovely music occurring at another point. And these two events, you might say one's before the other, or one's after the other, or they're simultaneous, and someone else can disagree about the relative times of them, so which occurred before the after and which occurred after the other. And we're going to show that with what we'll try to make a simple example, but this stuff does get a little complicated. So let's look at this. So we'll do a bit of a thought experiment here. So here are the conditions of the thought experiment. So I want you to imagine, and we've been talking about trains moving along quite a bit before. So we have a train with an observer in the train at position A in the train, and the train's moving to the right with some velocity relative to C. C is the person on the platform. Now these two people know that they're part of an experiment where when the front end of the train passes the front of the platform, there will be a red flash of light. So there's a red light bulb here, and when this passes this, when the front of the train passes the front of the platform, there will be a flash of light. When the end of the train passes the end of the platform, let's say, there will be a blue flash of light. So we can imagine these to be event red and event blue. Okay. Now what we're going to look at is how these two observers interpret this situation and when they think the two events occurred. So let's just step forward in time a little bit now. So a little bit later in time, because our train's moving to the right, as you can see, it is a little to the right relative to the platform. Now, if we imagine what's happened with the light, let's say that at this point in time, the flash has reached person A. The red flash, sorry, has reached person A. So it's passing like this. Now, at that point, the blue flash is here. Okay. Important thing I want you to note here is that the red flash has reached person A and the blue flash hasn't reached person A yet. So the red person sees the red flash before they see the blue flash. And I think that that will make sense to you here. I think that you can see that that makes sense as they're both moving in towards each other, but the train is moving to the right. So the train is moving towards the red flash but away from the blue flash. So the train will see the red flash before it sees the blue flash. Now let's step forward in time a little more, and let's say that at this point in time, the red flash and the blue flash have now both reached C. So they've got to here. Okay, so now C says, the red and the blue flash have reached me, and they've reached me at exactly the same time. So what does C conclude? C says, well, red and blue events occurred at the same time. And so let's just convince ourselves why they say that. It might look obvious, but let's make sure that we understand why that's the case. Well, person C sees these two flashes, and person C knows the conditions of our experiment. The conditions of the experiment being that the flash came from here. It came from the ends of the platform. Person C is standing exactly in the middle of the platform. So person C knows that the flashes have travelled the same distance. So the red flash has travelled from this end of the platform to himself, and the blue flash has travelled from this end of the platform to himself, and he knows that they're the same distance, and he can be sure of that because he has a set of coordinates like this one set up, and so he can very confidently measure what this distance is and what this distance is and be sure that they're equal. He also knows, and this was the thing that we covered in the previous vodcast, the second postulate of Einstein's, which is that the speed of light travels at c, and travels at c in all frames of reference. So he knows the speed of light, and he knows the distance, and he knows that speed of light is the same for the red and the blue flash. They're both light. So if they reach him at the same time, then simply, again, using this formula, so if this is our distance, then he can say that the time that's passed for the red flash to get from here to here is whatever this value turns out to be, and the time that's passed for the blue flash to get from here to here, which is the same distance, must be the same amount of time. Therefore, he concludes the two flashes occurred at exactly the same time. So I think that that is simple enough. Here's where it gets a little bit complicated. Let's go back to this position. So, sorry, before we go back to here, notice as well that at this point, for person A, they've seen the red flash, they've not yet seen the blue flash. So person A has said that the red flash reached them before the blue flash, and they haven't even seen the blue flash yet. And person A and C, they both agree on that. C can see that that's been the case. They can see that the red flash has passed A, but the blue flash hasn't reached there yet. They agree on that. But here's where it gets a little bit complicated. Remember Einstein's second postulate, which was that the speed of light is the same in all frames of reference. This means that as far as A is concerned, relative to her, the red flash is moving at the same speed that the blue flash is. Also, she knows the conditions of the experiment. She knows that the red flash went off when it was in line with the front of the train. The blue flash went off when it was in line with the back of the train. And that distance, so she also has a set of coordinates like this to be able to make very precise measurements of any event. And so she also knows that the distance from one end of the train, now I'm just going to use capital D here in case for some reason these distances are different. So I use lowercase d here, I'll use capital D here. We'll come back to that in another vodcast, but it's not entirely important at the moment. What is important is that she's standing in the middle of her train, and so therefore these distances from her to this end of the train, the front of the train, is the same distance as from her to the back end of the train. And she also knows that the blue flash was going to go off when the back of the train passed this point, and the red flash was going to go when the front of the train passed this point on the platform. So they both agree about those conditions. They agree that she sees the red flash before the blue flash, but she says that the red flash is coming at her at exactly the same speed that the blue flash is coming at her. So what's she supposed to conclude from this? Well, what she's supposed to conclude is she'll do a very similar calculation where she'll say the change in time, so this is the time that occurred between the flash happening and reaching her, is going to be the distance divided by c. So this will reach her, and she'll say, okay, the red flash occurred at whatever this value turns out to be. It occurred that long before. It's travelled that far and at this speed, so therefore the red flash must have gone off this long before. At some point later, which I haven't drawn, but you can imagine as the train continues to move, the blue flash will catch up and hit her, but it will happen after, and at that point she'll say, okay, now the blue flash has hit me, it's also travelled a distance d, it's also gone at the speed c. So therefore the blue flash occurred this long before it actually reached her. Therefore the only conclusion she can draw is that the red flash happened before the blue flash, which is to say that she thinks that the front of the train passed this point before the back of the train passed this point. And something I want to make really clear here is that this isn't a trick. They've just both made two measurements in their own frames of reference, and both are completely correct. And so the thing that we need to come back to is, although I haven't proved it in any of these vodcasts, and I said to go to the Michelson-Morley experiment if you want more detail on this, but the understanding that we're basing it on is Einstein's second postulate, which is that speed does travel at the same speed for all observers, regardless of their motion or regardless of the motion of the source of the light. And so that's absolutely true. And so the only conclusion that A can draw here is that the red flash occurred before the blue flash, which will take some time to get used to because it's very counterintuitive to what you're used to. But they are both correct measurements. They're different, but they're both correct. And this is what we mean by the relativity of simultaneity. So the final thing that I want to say about this is, as you can see, our times are varying based on motion. So that is based on our movement through space. And this is where the idea of space and time being connected comes from. And so you will have heard before people talk about space-time. And we'll go into more detail about this in the next vodcasts, but you might be starting to get a feel here for the idea that time and space are not fixed things. They change relative to the person observing, so relative to the frame of reference. So people often describe this as being like elastic. It can stretch and change. So in our next podcast, we will look at this sort of in more detail, and in particular, time dilation.